Okay, so yeah, let's get started with this very interesting series of lectures that Professor Paolo Pani has very kindly agreed to give to us. So a very brief introduction to Professor Pani. So Professor Pani has had a number of very important contributions to, in general, the field of astrophysical relativity, but also specifically to the topic of testing general relativity, especially with gravitational waves. So he's an associate professor of theoretical physics at Sapienza University of Rome. He's the principal investigator of the project ERC Dark Gravity, I believe. It's called Unveiling the Dark Universe with Gravitational Waves. He additionally got his PhD in 2011 from the University of Cagliari. He's the recipient of a number of prizes, including the SciGrav Prize in 2016 for Outstanding Referee Award. He is also a co-author on a few textbooks, including General Relativity and its applications, as well as superradiance. And he is a prolific writer in terms of scientific publications with over 130 of them. So without further ado, Professor Pani, I hand over the stage to you.
Okay, thank you very much, and thanks for this kind invitation. It's a pleasure to give these lectures. So I was asked to describe test of gravity, test of general relativity, and also starting with some basics topics, which I will cover in this first lecture. So I'll give 3 lectures today, tomorrow, and the day after tomorrow on test of gravity, starting from what are called the classical tests that have been used to test general relativity since its formulation more than 100 years ago. And then I will focus on more modern tests, and actually the kind of tests that are done nowadays to test the theories in different regimes. So the plan of my lectures is the following. So yeah, I first maybe apologize because I used to give lectures on Blackboard, so I'll try to use the Blackboard instead of sharing slides. And the 3 topics I will cover are essentially I will start giving some motivations today, why we want to test GR and how we want to test GR. And then I will discuss classical tests, kinematical tests that will become clear in a moment, and the topics on lecture 2 and 3 instead is devoted to gravitational wave tests in different regimes. I will mention some references, and well, I'll try to cover the basics, but I will also highlight open problems and recent developments. I will give some references to important reviews or important papers, and you can find these references and useful links on my webpage. I put a link to these school lectures, and there you will find several links that will maybe update in the next few days. And you will also find a link to some resources from our group webpage, in which you will find notebooks and codes that might be useful later on during my lecture. So I invite you to go there and explore with the material that you will find. Okay, so let me start with an introduction. So we want to test general relativity, which means we want to test a theory that can be described by an action that can be written in the following way. So this is the Einstein-Hilbert action, which describes gravity in vacuum. This is the Ricci scalar that depends on a metric. So G mu will be the metric. C is the speed of light. G is the gravitational coupling. And in most of my lectures, I will use units such that G equals C equal 1. So from essentially from now on, I will drop these units here, and masses and length and time will be measured by the same units. this is the action of general relativity in vacuum. The full action is the Einstein-Hilbert action plus the action of matter field, any kind of matter field that we can collectively call psi, and this action depends on these matter fields and the metric. In this way, the theory is uniquely determined, both in terms of the vacuum theory and how it couples to, say, any kind of matter fields. And from variation of this action here, we find Einstein equations, which is what we want to test. So let me write it for once with the correct units. So this is the Ricci tensor. This is again the Ricci scalar. Both are written in terms of the metric and its derivative. And this is the stress energy tensor that describes the matter. So in my lecture, I will drop completely the cosmological constant. So as you know, here we can add a contribution from the cosmological constant that will appear here as an extra term plus lambda g mu nu that I will neglect completely because I will focus mostly on tests in the using compact objects essentially. So in a local universe when cosmological effects can be negligible. Of course, they are very important in very different contexts, and maybe I will mention them in the next lectures. So we want to test this theory, well, this theory already comes from a series of principles and assumptions that, I mean, each of them can be tested and scrutinized to see whether the theory is correct or not, or at least relies on correct basis. So first of all, is a theory, of course, in 4 space-time dimensions. So we are studying space-time in 4 dimensions. It's a metric theory, which means that space-time is described in terms of a metric tensor that both describes the gravitational field and gives our manifold, so our universe, our space-time, a metric structure. So it allows us to compute angles and length in a proper way. And in fact, the line element of our manifold can be written as d squared, g mu nu, the x nu, the x nu. So once we can solve for Einstein equations, we will know the metric g mu nu, and from the metric g mu nu, essentially we know the metric properties of the space-time and how particles move in space-time. Indeed, let me actually erase here. Indeed, from Einstein equations, taking the divergence both left and right side, we know that the covariant divergence of t mu nu 0, which automatically gives geodesic motion. So the fact that point particles follow geodesics, which can be written also in this form here, where u is the particle for velocities. So as a crucial ingredient of general relativity, point particles, both massive and massless, follows geodesics of the space-time, and this is described by this equation, which is essentially the geodesic equation. And also this aspect of the theory is not trivial in the sense that it could occur in different theories that point particles do not follow geodesics, or maybe follow geodesic of a different metric, not the one described in the gravitational field. It happens so that in GR, they follow geodesics. It's one of the fundamental assumptions of the theory. And indeed, the fundamental assumption of the theory is what is called equivalence principle, which is one of the big pillars we want to test in GR. So this principle was a guiding principle for Einstein, and it exists in many different forms. And I'm sure that during the public lecture that Professor will give in a few hours, you will learn much more about it and about ways to test it. But let me just mention for the purpose of my lectures that there are at least two versions of this equivalence principle. One is what is called weak equivalence principle, or WEP, which essentially is the equivalence between the inertial and gravitational mass. And the weak equivalence principle essentially can be stated by saying that point particles follow in the same, the trajectory of point particles is independent on their structure, so especially on their mass, and they all follow geodesics in the same way. And this is the standard starting point of general relativity, the fact that independently on the mass, objects fall in the gravitational field in the same way. Then there is a strong version of the principle, so-called SEEP, strong equivalence principle, which tells us that not only is the weak equivalence principle valid, but also finite size objects such as stars or maybe black holes, their trajectory is independent on their internal structure. And these are much more non-trivial principle, in the sense that many theories of gravity might satisfy the weak version of the equivalence principle, but not the strong version. Actually, most of the theories that we study so far, the modern modified theories of gravity, do not satisfy the strong equivalence principle, while they satisfy the weak equivalence principle. The reason is that there are very strong, stringent constraints on violations of the weak equivalence principle. So we know that point particles have essentially an inertial mass that is very well equivalent to the gravitational mass within 1 part in 10 to 15. This is the most stringent constraint coming from the microscope satellites, a measurement done a few years ago. And so within 1 part in 10 to 15, which is really impressive, the inertial mass and the gravitational mass should be the same. So the weak equivalent principle is satisfied extremely well, and is one of the pillars upon which building modified gravity theories also. The strong equivalence principle instead is very different, because, for example, anytime there is an extra field, well, not any time, but most of the time, if there are extra fields in the theory, the strong equivalence principle might be violated. For example, in so-called scalar tensor theories, compact objects might have a scalar charge, and depending on the scalar charge, they might, essentially, their dynamics can be different with respect to the case in which they don't have scalar charge. So the internal structure matters for their dynamics. And testing the strong equivalence principle is one of the most important, say, cornerstone of test of general relativity. Okay, so having said this introduction, what we want to do now is, well, giving motivation why we want to test it, because of course these are fundamental principles, but why do we want to test them so thoroughly? And well, there are many reasons. So let me start by mentioning the motivations. So there are different kinds of motivation. Some are purely theoretical. So the theoretical reasons are that, well, we know that general relativity must be an effective field theory, and the reason is that at scales in which quantum gravity effects or quantum effects are important, general relativity is not expected to be valid, because it's a classic theory, and we don't know how to, well, yeah, I mean, there is no unique proposal for a quantum theory of gravity. So for sure, we want to test these aspects. So one is quantum gravity. The other theoretical aspect is that GR itself predicts the existence of singularities that are in general problematic. So are, well, they are not even regions of space-time, but anyway, they are concepts in which the theory itself breaks down and loses predictability. So for sure, we expect that near singularities, the theory has to be modified. We know from the theory, the theorem by Hawking, Penrose, and others, that singularities generally form in general relativity. Hopefully, they are covered by event horizon, so they only exist within black holes, essentially. Well, first, this is just a conjecture that should be tested, and second, is still, from a theoretical point of view, disappointing that there are singularities, and we should resolve them somehow in a more generic theory. Then there is a, say, observational motivation related to the problem, the infamous problem of dark matter and dark energy, which might be sort of solved in the context of beyond standard model physics, so including new particles, or in the case of dark matter, or a cosmological constant in the case of dark energy, but they might also find other resolutions in modified gravity. So instead of modifying, say, the matter sector, modifying the gravitational interaction at those scales, which are essentially galactic scales or cosmological scales. And there are hints, for example, in the tension on the Hubble constant that we know nowadays, that at least at the cosmological level, GR might not be a totally satisfactory theory. So these are very strong motivation, of course. And then there is a more phenomenological motivation related with the fact that there are several regimes in which we want to test the theory. And these regimes cover several orders of magnitude. So GR may be a correct theory or a satisfactory theory in a regime, but not in some other energy scale. And a very important diagram that one might have in mind when considering tests of gravity is a two-dimensional diagram in which here one can put the gravitational potential, let me call it phi, and this gravitational potential is essentially m over r, where m is the mass of a typical source, is a mass scale, r is a typical distance scale. And here one can put, let me call it capital C, the curvature, which can be written as m divided by r cubed. So the curvature is a dimension of 1 over a length squared. So it scales like 1 over r cubed. So it's a two-dimensional diagram, and different sources that we are gonna use to probe gravity populate this diagram in different places. For example, the sun, so solar system test, probe a potential which is at the level of 10 to minus 6 and a curvature which is at the level of 10 to minus 28. 10 to minus 28, this is centimeters minus 2. So while this number is dimensionless, the curvature has dimension. And here is essentially solar system test. What we are gonna discuss mostly, say from tomorrow's lectures, are instead tests what are called, so these are called weak field tests. What we can probe here with, say, neutron stars and black holes are what are called strong field tests, where the potential is of order unity. So there are 6 orders of magnitude. There is a jump in 6 orders of magnitude between solar system test and compact object test. And the curvature itself can range from, let me see, 10 to minus 13, something like 10 to minus 13, 10 to minus 30, depending on the mass of these objects. So neutron stars are, and solar mass black holes are associated with a curvature that one can compute from this quantity here, which is at the level of 10 to minus 13 centimeters minus 2. Supermassive black holes instead are down here. So objects with mass say 10 to 8, 10 to 9 solar masses have a curvature which is much smaller by, say, several orders of magnitude. And the reason is that the curvature at the horizon is essentially, from this relation here, scales like 1/m squared, mass of the black hole, and therefore the bigger the black hole, the smaller the curvature that it can probe at the horizon. And this is an important point to take into account, because while compact objects probe potentials which are effectively strong fields, so of order unity, when post-Newtonian theory potentially breaks down, they might or might not have a curvature scale bigger than solar system tests, because, well, depending on their mass, they can have either a bigger or a smaller scale. But so the important point is, as you can see, here there are 17 orders of magnitude, here there are 6 orders of magnitudes. Cosmological tests are down here, starting at curvature, I've written this down, 10 to minus 57, which is roughly the curvature associated with the inverse Hubble length squared. So you can see there is really a huge variability in curvature and potential that one can probe. And we have tested gravity in many different regimes, but it's important to not to leave any stone unturned. Okay, let me see if I want to say something else about this. No, not really at the moment. Okay, so the well, yeah, let me say just something. Now I will focus for this first lecture now on with field tests mostly, not only. Yeah, because I was asked to start from the very beginning. What we are testing right now with gravitational waves, of course, are mergers and highly dynamical situation involving neutron star black holes. So we are testing this curvature here. What future gravitational wave experiments, such as the LISA space antenna, will test are also supermassive black holes, so this corner or the parameter space, and also the famous silhouette or shadow of a black hole is probing the geodesic structure near a supermassive black hole or of billion solar masses, probing this regime here. So testing gravity with different probes is really something complementary, because we are testing different aspects of the theory. And an important distinction that one wants to make is distinguishing between what are kinematical tests that essentially probes the geodesic structure of the theory and the fact that maybe particles follow geodesics, and dynamical tests, which instead study the dynamics of the theory. For example, gravitational wave emission, absorption, and all dissipative effects. So these are different aspects that the test of gravity should take into account. Okay, so I forgot to mention that, well, if you want to ask questions, please feel free to interrupt me without any problem. And if you want to find a detailed version of this diagram here, this is taken from, is an updated version of Southeast, I think is 2009 paper, and there is an updated version in Baker 2013 paper. So a very nice version of this diagram is in those papers there. Okay, so this is why we want to test gravity. Let me now say how we want to test gravity. So from the theoretical point of view, one way to do it is to find a sort of systematic way to study modifications of general relativity. And a nice way is to use a theorem due to Lovelock that essentially singles out general relativity as the unique theory of gravity under a certain number of assumptions. And Lovelock theorem tells us that in 4 space-time dimensions, the only tensor which has covariant for divergence identically vanishing, which is symmetric, and is written only in terms of the metric, its first derivative, the second derivative, and also preserve diffeomorphism invariance, which essentially is associated with the fact that we are free to choose any reference frame to describe our theory. And what else? Let me see if I forgot some. Well, yeah, and it's rank 2. So it's a rank 2 tensor. The only tensor with these properties is really the Einstein tensor. So G mu nu is equal to R mu nu minus 1 over half R G mu nu plus possible the cosmological constant that I'm not including right now. So these are powerful theorem because if we believe in these assumptions, it tells us that we must have general relativity. But on the other hand, we can also uplift each of these assumptions, and by breaking each of them, we get classes of theories that we want to start. For example, if we start with log-logs, we can, for example, assume that our space-time is not living for the space-time dimension, so consider higher dimension gravity. So D is not 4 or greater than 4, and this opens the possibility of many different theories in higher dimensions, and we want to test, for example, the existence and the scale of higher dimensions. Another option is to assume that the weak equivalence principle is broken, and this has to do with this assumption here, because this assumption of log-log theorem guarantees geodesic motion, as I was saying before, because the T mu nu is conserved. And so in this case, we don't have geodesic motion, and T mu nu is not 0. And as I was saying, there are theories studying these possibilities. They are very strongly constrained, so I will not discuss them in much detail here. Another option is breaking diffeomorphism invariance, and there are two big classes of theories that break diffeomorphism invariance of general relativity. One is massive gravity. So in massive gravity, well, the graviton anyway, the perturbations of the theory do not propagate at the speed of light as a massless spin-2 perturbation. It's a massive perturbation which in principle should propagate 5 degrees of freedom instead of 2, so there are more polarizations. And this breaks diffeomorphism invariance in the same way as, say, a massive photon would break the gauge invariance of electromagnetism. Another option is Lorenz symmetry breaking. For example, by introducing a preferred time foliation, or a preferred space direction in space-time. So this breaks Lorenz invariance, and there are theories, also proposals for quantum gravity, renormalizable theories such as Java gravity, that are based on Lorenz breaking operators in the action. And finally, there is a very important assumption that is essentially at the root of most of modified gravity theories, is that the Einstein tensor is built only on the metric, but a possibility is to include extra fields. These extra fields can be dynamical, so they have extra degrees of freedom. They might also be non-dynamical, and then they modify the matter sector. But nevertheless, if we include the possibility of having extra fields, which can be scalar, vectors, or whatever, the assumption of Lovelock theorem are not anymore valid, and we might have different theories. For example, scalar tensor gravity, or scalar vector tensor gravity, or coupling, which are not possible between, say, curvature invariants and scalar fields and other things like that. And in these theories, typically the strong equivalence principle is violated because of the presence of extra fields. And of course, other things can be violated. For example, there can be extra fields that describe extra dimensions. There can be extra fields that describes theories with diffeomorphism invariance. So there might be some overlap in this classification, but the important point is that essentially Lovelock theorem tells us that we need extra fields most likely if we want to modify gravity at least in a simple way. Okay, so now the question is, after we understand that, how and what exactly we want to test of the relativity. And so now I would start sort of overview of the test of gravity that has been done essentially since the very beginning, starting from textbook material, the classical test of gravity. Then today I would also like to discuss two other effects, which are frame dragging and test of essentially the spin angular momentum coupling, and also test related with the geodesic motion in the strong field regime, like the black hole shadows. And then tomorrow and the day after, I will focus on gravitational wave test.
Professor Pani, I have here a question from one of the attendees in the chat, so I will just read this out to you. Sure. In which of these branches, exceptions to the Lovelock theorem, fall theories like f of r? Which assumption do they break?
Okay, yeah, so this is a good question. So f of r considers a theory like essentially an action written in this form, where this is a generic function of the Ricci scalar plus a matter action that depends on psi and the standard metric here. So this is the standard version of f of r gravity. This is in 4 dimensions, so it satisfies this. It satisfies the weak equivalence principle because matter is minimally coupled to the standard metric. It does not break diffeomorphism invariance because, well, the action is invariant under diffeomorphism, but it does break this assumption here because this theory is equivalent to a scalar tensor theory. So one can introduce a scalar field that it depends on the Ricci scalar and rewrite this equation in an equivalent way at the level of the equation of motion, in which there is an extra degrees of freedom. So for in f of r there are 3 polarization. 2 are, say, the standard gravitational one. Then there is an extra degrees of freedom due to the scalar field, and for this reason it follows in this category. Actually, the same is true if one considers f of r in the so-called Palatini approach, in which the Ricci scalar, I mean, in which the metric and the connection are independent. And in that case, one again gets an equivalent scalar tensor theory in which, anyway, the scalar field is not dynamical. And also in this case, I mean, there is an extra field that modifies the coupling to matter, but in a different way. Anyway, f of r gravity follows in this category. Okay, so after this introduction, let me now start with, so let me see if I want to say something else. I think not. Well, let me just mention this because I think at this stage is important. A very important class of theories that one wants to study is one in which the Lagrangian contains the standard Einstein Hilbert action, term, and maybe couplings that depends, for example, on higher curvature corrections, like these kinds here. And the reason is that these theories introduce a new coupling that is dimensionful. Is dimensionful, so it means that the theories modify generativity only in certain regimes, in particular at high curvature, where the curvature state is set by this quantity here. So this is a curvature square, so the dimension of alpha is a length squared that gives us essentially the length scale of the modification of gravity. And this is particularly important because this effect might be negligible at low curvature, for example, in the solar system. They might be important at high curvature, for example, near a black hole or within the horizon of a black hole near to the singularity. So this is a class of theory that is called, I mean, there are many other terms that one can consider, and it is called quadratic gravity. And again, it follows in the category of extra fields because one can rewrite this theory in terms of GR plus extra fields, or typically what one does is also considering the coupling between an extra scalar field and these higher curvature terms, which gives rise to what is called Einstein scalar quadratic gravity. And therefore, there are extra degrees of freedom in this case as well. So this is something I will discuss also for what concerns modified black hole solutions tomorrow. Okay, but before going there, let me really go back in the first days of general relativity and discuss what are called the classical tests of GR. They are called classical because many of them actually were proposed by Einstein himself right after the formulation of the theory, and they were the basis for test of general relativity. And I'm sure that Professor Will discuss the history and the long journey to test the theory based on this test. But I want just to give you some flavor of what these tests are. So the very first one is probably how can I call it? The gravitational ratio. And I also want to discuss them. Of course, I will not present them in any detail, but I also want to discuss mostly what exactly do they test of a theory and whether they test really general relativity or some sort of say subset of the assumption that are behind the theory. So the gravitational ratio is the fact that the frequency of radiation emitted by a source in a gravitational field can be measured differently by an observer at infinity. So one can consider a source, say of mass m, say radius r, and say a massive source, and then a source of electromagnetic radiation, let me call it source, that emits radiation, and this radiation is then detected by an observer at infinity. And one asks, what is the frequency observed by this observer at infinity with respect to the frequency emitted at the source? So
Professor Pani, sorry to interrupt you. I just wanted to mention that the one that you have written is actually falling outside the screen on the left. If you could maybe just center it just a little bit.
Okay. So how about this?
Yes, that's good. Yeah. So everything to the right of that will work. Yeah.
Okay, great. Thank you. Okay, so a crucial point is what I already wrote at the beginning, that the line element that gives us the invariant four-dimensional distance in the manifold is written in this way in terms of the metric G mu. And when we want to essentially discuss frequencies and periods of an emitting source, we want to talk about proper time. And the proper time in this case is just d tau squared equal to minus. So the proper time is the time measured by an observer which is moving together with the source. So all these terms here are 0 except for the time component, and this guy will be therefore g naught naught that it's not squared, or let me call it dt squared. Okay, which tell us that the, let me call delta tau source, delta ts is equal to square root of minus g naught naught delta t source, and the delta tau observer is square root of minus g naught naught at the observer location, and these are the source location, delta t observer. Okay. So the proper time, this delta means, for example, one period of the emitted radiation, is just the coordinate time times this square root of the g naught naught component of the metric. And in a stationary field, assuming a stationary field, these quantities are the same, and therefore one gets the famous ratio formula, the delta tau observer is equal to delta tau source square root g naught naught source divided by g naught naught observer. Where do we see? Right. Yeah, okay. Okay, wait.
It's the other way around.
Yeah, it should be the other way around, right? Yes, thanks. Observer source, because the final result is that the frequency of the radiation observer is square root of g naught naught source divided by g naught naught observer. So it's the inverse of what I just wrote, times the emitted the frequency of the emitted radiation. And for an observer that is very far away, this guy is essentially almost unity, and what one gets is square root of 1 minus 2m r source nu s, where I use the fact that g naught naught, let me write it here, for a Schwarzschild metric is minus 1 minus 2m over r. Okay, so in this step here, and only in this step, we are assuming that the metric of a spherical symmetric object is described by the Schwarzschild metric. But in fact, if we are looking at this effect only for in the weak field limit, this is essentially true in general, because in the weak field limit, the g naught naught can be always be written in terms of minus 1 plus 2 phi divided by c squared, where phi is the gravitational potential in Newtonian theory, so it's minus gm divided by r, and therefore any theory which is essentially gives a metric that is totally flat, so if any theory that recovers Newtonian gravity in the weak field regime will have this behavior here. This is to tell that what the gravitational ratio in fact tests is an effect of essentially any metric theory with a gravitational I mean, that reduces to Newtonian gravity at large distances, at least if one tests the gravitational redshift in the weak field regime. Of course, in the strong field regime, what in fact is testing is the structure of the G time component of the metric. For a solar system test, if one considers a source emitted very close to the sun, this quantity here is just 2m divided by radius of the sun. We are very well in the weak field regime, and in fact, this quantity, if one measure the, right here, if one measure delta nu divided by nu, so delta nu is the difference between the observer and the source frequency. This is roughly in the weak field regime Gm c squared r, where r is the radius of the emitted, and for the sun, this guy is 10 to minus 6. Is the quantity that I was mentioning before in that two-dimensional diagram. So it's a small effect, and of course it will become much bigger close to the surface of compact objects, in particular for a source emitted at the horizon of a Schwarzschild black hole, so r equal to n, this guy is 0, so the horizon is an infinite redshift surface, because radiation emitted very close to the horizon is totally redshifted towards 0 frequency. And so, in this quantity was, well, first test already in 1925, if I'm not wrong, by measuring the gravitational redshift of Cyrus B, one of the first white dwarfs that have been observed. And I mean, this shift of the emitted lines was observed to be in agreement with general relativity, but in fact, as I was saying, with anything that will have a metric theory reducing to Newtonian gravity. Okay, also an important point to keep in mind is that there is only essentially one-dimensional number in this test that we are studying, because if you are taking a source of mass m and a typical length scale, say r, the only dimensionless quantity we can measure is m divided by r, and therefore each of these quantities that I'm mentioning now for the classical test will always be of order m over r, which is something important to keep in mind, because if you change the theory, maybe the prefactor in front of this number might change, but in fact you are testing always things which are of order. Okay, so
Professor Pani, can I quickly ask a question here? So I was just wondering, for this particular test where you talked about the light from a star that is getting redshifted by the sun, would we have to account for the proper motion of the solar system with respect to the star, or is it much smaller than the kind of shifts that you get from gravity?
Well, I guess that the answer is, well, it depends on the relative velocity, because this effect, for example, as I was mentioning, is of the order of 10 to minus 6. The standard Doppler shift that one would expect because of different relative velocity scales like, let's say, V divided by C, I believe, probably squared. But yeah, anyway, if this number or the square of it is bigger than 10 to the minus 6, then it's an important effect. So it depends on the relative velocity of the source. If it is much smaller, of course, this would be the dominant effect.
I see. Thank you.
Okay.
So I see Professor Sriram Kumar has a hand raised. Would you like to unmute and ask?
Hi, thank you, Shashwat. Actually, I have two questions. One is when you talk about weak or strong field limits, you are talking about essentially phi by r, the ratio of the Newtonian potential to the radius. Is that correct? Its value.
Yeah, in this context, weak versus strong would be whether the gravitational potential divided by c squared, which is dimensionless, so it's g m c squared by r. It's either much smaller than 1, and then it would be weak field of order 1, and there would be strong field.
So when
order is also curvature, but that's a different scale.
That is what I was concerned about. You know, in a cosmological context, you may, if you don't have a potential and you want to talk about strong or weak field regimes, is that reasonable to speak about?
Well, in that case, well, you can still define, say, this as a perturbation on top of the, say, Friedman-Robinson-Walker metric, and it tells you whether you are in the linear regime or not. In that case, I guess that in cosmological context is more relevant to talk about the curvature scale, so the vertical axis I was drawing before, because that tells you, yeah, I mean, the curvature that you are probing depending on which epoch of cosmology you are looking at.
I understand. The other question I had relates to the different theories you talked about. Do you make a distinction between general covariance and, you know, a theory being invariant and a diffeomorphism?
Let me see. I would say that I was using them more or less in the same, with the same meaning, in the sense that yeah, when I was saying diffeomorphism invariance, I meant the theory is can be written in any reference frame. So any reference frame can even accelerate. So there is no preferred or spatial or time direction. And a natural way to implement this is using the principle of general covariance. So essentially writing the equation in tensorial forms. It might not be necessary in the sense that you might also find a theory which does not have a tensorial form and still satisfies the diffeomorphism invariance. I actually, yeah, I mean, I don't know any example right now, but in principle it's possible, yes. But anyway, by diffeomorphism invariance, I meant that there is freedom to change coordinate frames arbitrarily.
Yeah, thank you.
Sure. Okay, so another classical test, a very standard one, is the light bending. Let me just mention briefly what the classical test is, also because this is totally superseded by what nowadays we test in general relativity. Because I mean, the fact that light bends is at the basis of, for example, gravitational lensing that is used in cosmology routinely, but also on the images that we get from, for example, supermassive black holes. And so essentially it's really at the core of the theory. So historically was tested in the solar system regime, but is nowadays tested everywhere. And it's the fact that light follows geodesics, and and geodesics depends on the space-time. So a massive source deforms space-time, and therefore geodesic motion is affected. And this was tested. Well, I don't want to spend too much time on this, but this was tested by considering a source of mass m and radius r, and a light moving in the space-time of the source. In Newtonian gravity, light coming from infinity in this direction will just follow a straight line with an impact parameter b, when r is equal to b sine phi, where, say, this is the coordinate r and this is phi. Okay, and b is the impact parameter. what happens in GR is that light feels the attraction of this mass here, and therefore light is bent with an angle, let's call it delta, that is non-zero, and as you would expect, delta is dimensionless, so it must be of order m divided by r. Okay, and well, in GR we can compute exactly the prefactor of this quantity here, which might be different depending on the theories. And here what one can do is to study geodesic motion. And let me just quickly mention, so I will sketch the derivation. So for geodesic motion, here we are interested in two quantities. So phi dot, where by dot I will mean derivative with respect to some affine parameter of the trajectory. This is L divided by r squared, where L is the angular momentum of the orbit, and r dot squared is equal to E squared minus 1 minus 2m over r L squared r squared. So these are the two equations of motion that one uses for massless particles. So this is massless because we are talking about photons. That comes directly from geodesic motion. And of course, as you can see here, there is a factor that depends on the Schwarzschild geometry. If the geometry is not Schwarzschild, this might be in general different. And well, in general, the geodesic motion is a combination of the GRR and GTT component of the metric. So one can use this equation, and it's easy to see that if one defines a variable u equal to 1 over r, then these equations can be written in this form. U second plus u equal to 3m u squared, where u prime is the u d phi. So one gets this simple equation, and the simple way to solve it is to solve it perturbatively when this term is small compared to the rest, because it's a small correction. So in the weak field regime, again, one gets u equal to, if I'm not wrong, 1 over b sem phi, which is the zero order 10 Newtonian gravity, plus a correction. And this correction, well, I'll leave as an exercise to solve this equation. Well, yeah, the solution is not crucial, but let me call it that u phi. It can be solved perturbatively entering the solution here, and the deflection angle from this drawing here is defined by the fact that u phi plus pi, sorry, ud of delta plus pi, so this angle here is equal to 0 because it's 1 over r. So r at infinity is delta plus pi, and this, by solving this equation here and plugging this condition, one gets delta equal 4m divided by b, I guess, yes, the impact parameter. And this is the standard deflection. It's interesting that actually in any metric theory of gravity, so if one really does the computation from beginning to the end, one can realize that this 4 comes from two contributions, in fact. One is common to any theory of gravity, and is just due to the fact that light is bended because of the geodesic motion. But then there is an extra term that is really a prerogative of essentially of the metric that we are considering, and in different theories of gravity will be different. And so the combination of the two gives precisely this number here, which is what has been tested in GR. And well, I'm sure that you will know the first test of this was done in 1919 by Eddington during an expedition and during a solar eclipse, and essentially was measuring the light deflection by the sun of some star that was not visible normally because it's covered by the sun luminosity, but during an eclipse one can measure the deflected, the apparent position and compare it with the true position of the star, and this was tested by, say, 10%. It's interesting that a similar eclipse occurred 100 years after this expedition, so 3 years ago, in 2019, I think mostly in North America. And well, people have done this experiment again with much better instruments, and the very same experiment was confirmed at the level of 1%, more or less. Of course, it's a tough experiment because it's a small effect. Again, for the sun, this is a deflection angle of 10 to the minus 6, so it's really tiny, but nevertheless possible. So a question that might be interesting is what kind of theories are we testing, and what kind of deviations from GR are we testing? And I'm sure that in the public lecture that you will have in a few hours, you will know more, but a very nice way to test, to implement classical test of GR is by using the PPN formalism, the so-called PPN formalism, which stands for parametrized post-Newtonian formalism. And this was developed by Norderth and Will himself to test generativity. And the idea is that one can consider post-Newtonian corrections, so corrections to essentially the two-body problems that are relativistic in terms of, in the sense of an expansion of v square over c square much smaller than unity. And the post-Newtonian approach is something routinely done in GR, and I will mention it tomorrow more in detail. But the idea of the parameterized post-Newtonian formula is to parameterize deviations from the standard post-Newtonian theory in generativity by some parameters. And there is a finite number of parameters that can be added, and they essentially parameterize all theories in the weak field regime, of course. There are, say, around 10 parameters, 10 PPN parameters. And for example, the first ones are those in which the line element for metric theories of gravity can be written in this form. Let me see. Well, let me write actually this way here. So the GTT is minus 1 minus 2m over r plus, if I'm not wrong, beta minus gamma m squared r squared. Let me see if I wrote it correctly. What is that? Yeah, there is a factor 2 here. Okay, and then plus, of course, higher order corrections that I'm not writing. And the GRR is expanded 1 plus 2m gamma divided by r plus other terms. So this gamma and this beta are PPM parameters. And it's interesting that the expansion of the GTT, the leading order in 1 over r, so this guy here, this is the gravitational mass. While it can be proved that the expansion of the GRR at large distances, this guy here, is the inertial mass. So in a sense, gamma can be thought as a parameter that tells us the difference between the gravitational and inertial mass for a source that is finite size. So it's not just a point particle, it's, for example, it's the sun. And of course, GR is recovered when gamma is equal, beta is equal 1. So in GR, the two masses are the same. This expansion gives the same coefficient, which is the mass of the space-time. And this quantity are equal to 1, so this guy is 0, and you don't get this correction here. So for example, the gravitational redshift measure only this correction, not this one here. So the best it can done is putting a constraint on the combination beta and minus gamma. The light bending instead puts a bounce also on this gamma here. So as I was saying, this factor 4 comes from a sort of universal correction in any metric theory of gravity, plus a correction that depends on gamma, which is proper of the theory, because in GR gamma is equal 1. In other theories, you'll have a different number. And when one can work out, in general, given this parameterized post-Newtonian expansion, this correction here, and work out the factor, there will be a correction 1 plus gamma, if I'm not wrong, that reduces to GR when gamma is equal to 1. So this is the kind of constraint I want to put. Of course, as I was mentioning, the effect is small in the solar system, but right now we are probing this much better, and in a moment I will discuss the silhouette of a black hole in which light bending is crucial and is actually way stronger than this effect. Is of order 1 effect. So effectively, this is totally superseded by current observations. Okay, I mean, for completeness, let me mention another effect, and I also want to use this as an excuse to tell you how far we went beyond classical tests. And one of the classical tests of GR, which was also one of the motivations, maybe the only one, the only phenomenological one to test, to modify Newton theory at the time of Einstein, is the periastron advance. And as we know, there was this discrepancy in Mercury's orbits. The periastron was advancing differently than one expected in Newtonian theory, because an important point to keep in mind is that the periastron advance of Mercury exists also in Newtonian gravity due to, for example, third body interactions and other effects. But also even taking into account all of those corrections, there was still a discrepancy that was explained beautifully by Einstein and his theory. And here, the way to study periastron advance is again studying geodesic motion, but for massive particles this time, because Mercury can be thought as a point particle in the orbiting the sun. So for massive particles, the equation that I wrote before for the variable u is something like this, but there is an extra term. Let me tell you. So this is something that you will find by studying the geodesic world. Divided by R cube. Okay, so this is the equation of motion for Mercury orbit if one assumes, well, this is valid actually in general, if one assumes that Mercury is a point particle. So these extra terms is what is coming from the fact that the orbit is massive. In the massless case that I was mentioning before, there is also such a term. And one again can solve this equation perturbatively, starting from a Newtonian orbit. So at the leading order, the orbit is just an ellipse, as in Kepler's law, plus a correction. And what turns out, well, let me write you the solution. So UD phi is, well, I'll write it completely.
Shouldn't the right-hand side have u squared?
Yes, thank you. Yes, it's just like before we had this extra term. Thanks. So the full solution that you can find perturbatively, perturbatively is this one here, where E is the eccentricity of the orbit, cosine of phi minus 1 minus 3m squared by L squared. Sorry, at the end of the blackboard. So this is the full solution already at the perturbative level. Of course, when the eccentricity is 0, the orbit is circular, so you don't get any periastron advance. But when there is eccentricity, you get periastron advance because the periastron is defined anytime this cosine is equal 1, because u, remember, is 1 over r. So when u is maximum, r is minimum, and you are at the point of closest approach to the sun, in this case. And therefore, this occurs when this argument, cosine is 1, when this argument is 2 pi times an integer. And what you get from here is that there is a periastron advance that gives you, for each orbit, 6 pi m squared L squared. And the same that you write here, L is the angular momentum of the orbit, which can be related with the periastron itself. And the final result is 6 pi m 1 plus E divided by RP, which is the periastron distance. So again, is an effect which is linear in this ratio, as expected, independent of the eccentricity. And for Mercury, it is the famous 40. What is that? The 43, almost the 43 arc second per year. Sorry, per century. Which was precisely on the spot of the discrepancy that was found in Mercury to explain the anomalous periastron advance. And again, in modified theories of gravity, this guy will be slightly different because, again, this equation here depends on the components of the matrix. So this gives a post-Newtonian, parameterized post-Newtonian constraint. And also gives me the opportunity to mention that this is a tiny effect in the solar system. The reason is Mercury periastron, unit of the mass of the sun, I think is about 10 to 8. So this quantity is about 10 to minus 8. Is a tiny effect. For the Earth is even less because the Earth, the distance is bigger than Mercury from the sun. But the very same effect is much more important in relativistic binary systems. For example, in binary pulsar systems. They are much more relativistic because in that case, the mass is, well, is of the same order of the mass of the sun because the total mass of the binary system is, say, few solar masses. But the distance, the typical distance of a binary system, binary pulsar system detected so far is about 10 to 6 kilometers. And if you compute this quantity here, you will find that this correction, the periastron advance for a binary pulsar can be pretty important. In fact, I think that for the double pulsar binary that has been detected something like 16 years ago, if I'm not wrong, this effect is of the order of, say, order 10 degrees per year. So it's a huge periastron advance. So each year, the system, of course, in 1 year, the system might make many orbits, but each year there is an advance of the periastron by roughly 10 to 20 degrees, depending on the system. Of course, it's much more important. And in fact, binary pulsars are great tests, I mean, great probes of general relativity in the in a regime that is, of course, way beyond the solar system. And the reason is that at these distances, their velocities, the orbital velocities, are already mildly relativistic. And this is why effects that are tiny in the solar system are important for binary pulsars. And at this point, I want to mention just a few weeks ago, there was a paper which is this a sort of well, final word after years of measuring and timing the double pulsar, the double binary pulsar that has been detected, as I was saying, 16 years ago. And there was this paper by Kramer et al. I can give you the reference here, and it's also on the web page I mentioned at the beginning. And this is a paper in which essentially they give the summary of the many tests of general relativity that were possible with this system. It's an exceptional system for many different ways. And well, they were able to measure for the first time several effects. This effect is very important. It was measured before, but it's very strong in this effect, in this system, and also other effects that I will mention in a moment. Okay. So, yeah, I think, let me see. Well, let me just mention for completeness, but I won't go in any detail, the fourth classical test of gravity, that is the Shapiro time delay. So this was a more recent test. The previous ones were proposed right after general relativity. This was proposed by Shapiro in the 1960s. And the effect is due to the fact that radiation propagating in a gravitational field gets delayed. For example, if it's sent from Earth to some planet like Venus and coming back, there is a delay that can be computed just by taking into account, again, geodesic motion and the fact that the orbit is that the Earth is orbiting around the Sun. And there is an interesting point of this effect is that if one works out the computation, and this can be done essentially by considering a null-like geodesic, so where the S squared is equal to 0, and this gives you the fact that 1 minus 2m over r dt squared is equal to 1 minus 2m over r dr squared plus r squared dphi squared for a planar orbit. And computing this quantity here, so integrating this quantity in time, taking into account that phi and r are related by a given trajectory, for example, a straight line, if one takes to 0 the straight line, this equation can be integrated and one can find the delay time, coordinate time with respect to the initial point of emission and the point of reflection. An interesting point, if one performs this integral, is that there is a logarithmic correction that grows logarithmically with the distance of the, essentially of the point where the radiation is reflected, which is important because it tells you that the farther one can go, the bigger the effect. So there is a possibility to test better this Shapiro time delay. And this was done again in the 60s and also more recently by the Cassini probe, which tested this effect at the level of 10 to minus 5. And this is also the constraint that comes on the gamma parameter. So the gamma parameter can deviate from unity, the ppm parameter, at most in 1 part in 10 to minus 5, which is really impressive and is well, one of the best constraints on the ppm parameters that we have. It comes from the Shapiro time delay measured by the Cassini probe. Okay, let me now, so this was very standard. I want briefly to discuss 2 other effects. Maybe I won't have time to do it today. I will continue a bit tomorrow. But so let me mention. So let me, yeah, these that I'm going to discuss are not anymore classical tests in a strict sense because they are much more recent. So one is the black hole shadow. And the other one is the frame dragging effect that maybe is more classical, but I want to discuss it later in order to introduce spin effect in the theory. But so I will focus now on the case of radiation moving around, I mean, the strong field regime close to a spherical source for simplicity. So let me take, say, a black hole of mass m, horizon 2m. And one asks itself what is the silhouette, so the shadow that this object casts in the sky if illuminated. And there are two possible ways to essentially illuminate this object and observe the radiation that is then projected on the sphere. One is if there is radiation coming from infinity. And the crucial point here is that geodesic motion in relativity can be described by the equation I wrote before, r dot square equal to e square minus 1 minus 2m over r and square r squared. And you can define this as an effective potential, which has this form. So it goes to 0 at infinity. It has a maximum at 3m, and this maximum is called photon sphere or light ring, and is the location in which unstable circular photon orbit exists. So as an extreme light bending effect, photons orbiting at 3m can stay in circular orbit. They are unstable, this orbit, but nevertheless they exist. And this is why I was saying close to a black hole, light bending is extreme, much stronger than what we were discussing before. This potential has a maximum, which, if I'm not wrong, is L squared 27m squared, if I'm not wrong, which means that when the impact parameter of the radiation, which is just L over E, is smaller or equal to square root of 27, so the dimension 27m. When this happens, radiation is captured by the object. So essentially, this means that the energy is above this potential barrier, and therefore any radiation coming from infinity will fall down, will be absorbed by the black hole. So this number is important, is 3 square root of 3m, because it tells you that if there is radiation coming from infinity, that with an impact parameter of 3 square root of 3 would be essentially captured, well, exactly 3 square root of 3 would be captured by the object and will start, oh, sorry, this is wrong. Let me write it properly. So this is the horizon, and this is 3m, the photosphere. So radiation with an impact parameter of 3 square root of 3 would start orbiting the photosphere, lingering around it, and will remain in this photosphere orbit. Radiation coming from infinity with a slightly smaller impact parameter will eventually be absorbed by the black hole, maybe making several revolutions around it. And only radiation with bigger impact parameter is not captured and is scattered and it goes to infinity. So this essentially means that for a spherical symmetric object, in general relativity, the silhouette, so the hole, the shadow in the sky sphere that this object casts when illuminated from infinity is 3 square root of 3m. It's not the horizon, it's not even the light ring, which is 3m, it's slightly bigger because, again, light bending. Of course, in a modified gravity theory, this number is different because this equation itself will be slightly different. And again, one can put constraints, in principle at least, on this because this silhouette will have a different size. There are two main problems. One is that, of course, this is a simplified picture because in reality there is also spin that drags radiation in a way that I think I will discuss tomorrow because there is no time. And the second is that I'm talking about radiation coming from infinity, so this object is illuminated from infinity, but in reality, what we see from this silhouette is radiation falling, so it's the radiation emitted by matter, gas, plasma falling into the black hole from, for example, an accretion disk that is surrounding it. And so the computation that I've done is of course different. We want to study radiation emitted near the black hole, for example, at some distance r, and this radiation is emitted, and we want to study how it reaches infinity and which kind of pattern does it have. And of course, this depends on the details on the emissivity, for example, of the disk. It depends also on the way the disk emits, at which frequency, at which distance, and so on and so forth. So the computation is much more involved, but the key ingredient is essentially universal, in the sense that the details might change, but the shape, the gross grain shape of the shadow is the same, and depends on, of course, the mass, but also the spin of the object. An interesting point, and I will maybe close with this, is that one can compute the escape angle for photons emitted at a given distance r from the black hole. And in order to do that, well, I think I won't have time to do the computation, but the idea, well, it can be found in some of the references I put online. But so the idea is to consider what are called Fermi coordinates. So these are coordinates attached to accelerated observers, and because this radiation, these sources, matter around the hole is typically accelerated. So when it emits, you have to consider the fact that it's accelerated. If you consider this coordinate, you can compute in this coordinate frame the angle, let me call it psi, of, say, a photon emitted in a given direction. And it turns out that the escape angle, let me call psi-esque, is, well, I have the full results here, I'll tell you. Yes, it goes like square root of r minus 2m divided by 2m, by m. So this is the escape angle of the radiation. What it means that when this photon has exactly this impact parameter, it would go around the photon sphere. So let me write again here, otherwise it's unclear. So this is the object, this is 3m. Let me suppose that there is a source here close to the black hole that is emitting radiation. So this escape angle is the angle, the critical angle in which a photon emitted in this direction will eventually be captured by the black hole and orbiting the photon sphere. And what happens is that if we are very far away, the escape angle is big, because of essentially any photon is able to escape infinity. But interesting enough, the escape angle goes to 0 as r minus 2m goes to 0. In fact, what happens is that if the source is precisely at 3m at the photon sphere, it can be shown that this escape angle is pi. So it means that all radiation emitted in this direction goes to infinity. All radiation emitted in this direction is captured by the black hole. Radiation emitted vertically just stays around the photosphere at 3m. But then if we are very close to the black hole, so when r is, say, 2m 1 plus epsilon, then what happens is that the escape angle goes to 0. So radiation that is falling to the black hole when it emits very close to the black hole has only a very small escape angle to reach infinity. So not only is the radiation redshifted, as we were mentioning before, because it's emitted in a region when the gravitational potential is large, but it's also essentially almost completely captured by the black hole, because all this radiation eventually goes around and hits the black hole. When the escape angle is close to the critical value, radiation can make several revolutions around the photosphere and possibly escape to infinity. And this is associated with several images of the same source. So there are multiple images that that characterize the silhouette of the black hole, and is also related with the phenomenon of multiple sources, multiple images in the gravitational lensing. So this is due to the fact that radiation can be so much bent to orbit and revolve around the black hole several times, and each time produce a different images. Okay, so I think I'm out of time, so I will finish here, and tomorrow, before going to gravitational test, I will briefly discuss frame dragging, and this will close, say, what have been the kinematical test of general relativity, and I will then focus on dynamical aspects. Okay, so if you have any question, let me know.
Thank you very much, Professor Pani, for a very illuminating lecture. So I guess we have a question from the chat, which I'm going to read out to you here. Are there any factors missing in the expression for psi-esque due to get the pi/2 for r equals 3m?
Oh, yeah. So this was just the scaling, but I have here, I can write exactly the expression. I have it here. The exact factor is this one. Let me see if R is 3m, this is 1. Let me see. 3m, this is 1. 7, 3, 7, 5. Yeah, that. Oh, I will have to check and tell you tomorrow, because yeah, I wrote down this expression here, but it should give some. Oh, no, sorry. This is true. Yes. So this is not the exact expression. This is true only when R is very close to 2m. So it's already an expansion. The true expression is more involved. I don't have it written here. So yeah, it's more involved, but can be computed, as I was mentioning, by studying the motion of this photon, for example, in Fermi coordinates. And the expression is more complicated, but gives the final result that when R is 3m, sine of psi is 0, so the angle is pi/2. Yes. So this expression is valid only very close to the horizon.
Okay, so we have 3 other raised hands. So I guess I'll start with Professor Sriram Kumar. Could you please unmute and ask your question?
Thank you, Shashwat. Paolo, in the parametrized post-Newtonian expansion, you had written this expression for GTT and introduced these parameters beta and gamma. These will just depend on the theory of interest, these parameters?
Yeah, so these are generic ways to parameterize modification of GR. So the idea is that one does a post-Newtonian expansion in terms of post-Newtonian potentials, and the way these potentials enter then the metric, and contribute to find the solution, can be parameterized in terms of some dimensional numbers. Given a theory, the values of beta, gamma, and all the other ppm parameters is fixed. So yes, they do only parameterize. I mean, they do only depend on the theory. And in GR, they acquire a definite value that is typically either 1 or 0 by definition.
Thank you.
Okay, so the next person is Syed. So I'll unmute you here or allow you to unmute and then you can ask your question.
Hello, am I audible?
Yes.
Yeah, so I wanted to ask, can you just explain the difference, like why the shadow of the black hole was 3 root 3 and what was the difference between 3m and 3 root 3m, like why we were getting that and what do we actually see in our observations?
Yeah, so forgetting that, neglecting the spin and really taking spherical symmetry, the point is the following, that this is the horizon, 2m, this is, say, 3m, the photon sphere. So where circular photon orbit exists, but the gravitational, the potential that this photon sees is something like this. This is 3m. But the crucial point is, what is the energy that this photon can have in order to be for sure absorbed by the black hole? So if this is energy squared, this is really just a scattering problem. This is the maximum of the potential. And if I'm not wrong, this maximum is L squared divided by 27 m squared. It can be computed from the potential I wrote before. And what is the point is that if the energy is small enough, radiation coming from infinity will approach the black hole and then there is a turning point and go back. And this corresponds to orbit that does something like this, right? So they approach, there is a minimum distance, the periastron, and then they go again to infinity. Any orbit above this threshold is instead captured. The critical one is here, and when the energy is equal to this quantity here, and this condition gives you a critical impact parameter, which is precisely 3 square root of 3m. And physically, what it means that if your impact parameter is exactly 3m, so the photon is moving along this line, is for sure captured by the black hole because the gravitational attraction is such that it will go inside the photosphere and be captured. If instead it's outside the photosphere, it's emitted in this direction with a bigger impact parameter, it can still be captured unless the critical parameter is bigger than this number here. So if the critical parameter is bigger than 3 square root of 3, the gravitational attraction is not sufficient for the particle to be absorbed, and it will be just scattered away. So the fact that it's slightly bigger is due to the height of this potential, and to the fact that even when it's bigger than the photosphere, it can be still captured.
Okay, thank you.
Right, so we have one more raised hand, that's Srijit. So I'm going to allow you to unmute. Please go ahead and unmute.
Okay, so I have a question from this shadow itself. So I frequently found that this in the derivation or in the analysis of shadow, the observations are made in the equatorial plane. Mostly, in the analytical treatment at least. So theta equal to pi by 2 plane. So is it true? Is it a harmless assumption for all sorts of solutions, or is it how this can be?
To repeat the question, because the audio is not great here and I could not understand it.
Okay, so if we consider this Schwarzschild black hole shadow, so then this analysis assumes that the observation is made in the equatorial plane.
Sorry,
equatorial plane, theta equal to pi by 2 plane.
Okay, sorry.
Yeah. My question is how harmless this assumption is for generic cases.
Okay, so for a Schwarzschild black hole, it doesn't matter because being spherical symmetric, any plane is the equatorial plane. And this is related with the fact that orbits on Schwarzschild are planar for the same reason, because there is no preferred direction. Of course, this is just an idealization, because in reality, well, we know that the black hole that M87, the one that has been observed by the Event Horizon Telescope, is probably spinning, and most likely any black hole is spinning, even maybe if not very fast. And spin breaks this, so there are no anymore only equatorial orbits, and this complicates things quite dramatically, because orbits will be different depending on the details of essentially of the derivation. We expect that the accretion disk around a black hole is mostly equatorial, meaning that the distribution of matter follows an equatorial shape around the black hole. This is what comes out of simulations, but I mean, how thick the disk is, and therefore how much is the emissivity outside the equatorial plane, depends on the models. So it can be very, very complicated. For generic orbits, besides this constant of motion, E and L, angular momentum and energy that are conserved, in Kerr, there is a third constant of motion that, the Carter constant, which makes the system totally integrable. For black hole solution beyond GR, this is not true anymore. There is no integrability, so one has to solve the equations for sure numerically. Well, there might also be not equatorial symmetry, in the sense that, for example, the North Pole can be different from the South Pole, and this will modify the geometry for sure.
Can I just ask? Yeah, can I just ask? I mean, a related question. I mean, how do you interpret the Kerr result, where people I have seen has taken theta equal to pi/2 plane?
So the current result, well,
I understand that it is integrable, but when they write down the final expression, so there seems to be an assumption being made there also.
Yeah, no, I mean, I'm not sure what we are referring to when they write the final expression. The way the full computation is done is by computing different setups in which the spin, the orientation of this black hole with respect to us and the spin direction are different. And for each of these realization, there is a different, say, silhouette or shadow. And then matching the data, ideally what one can do is to find the configuration that best fit the data. A crucial point is that data so far from the EHT are not very stringent in terms of the spin, so the spin is almost unconstrained. There are indications, actually relatively strong indication, that the object is spinning in a given direction, but the spin itself is not very well constrained by these observations. So at this stage, at least, it's hard to make a definitive claim. In fact, zero spin, I don't think is excluded by the measurement, even though it's not the most likely option. So yeah, I think that the short answer is the spin in principle can be constrained. It is crucial to understand the shape, but currently is not very well constrained.
Okay, thanks a lot.
Okay, so I don't see any other hands raised, nor do I see any chats. So just to check one last time, are there any other questions? Okay, I'm going to take silence as a no. So once again, thank you very much, Dr. Pani.